Hello. This is the second to the last section that we're going to do in this chapter 7 on similarity, and I'm actually combining two sections, 7.6 similarity transformations and a section up in chapter 9 called Dilations. They're really one and the same thing, so I thought I'd merge them together. As we mentioned in class today, I'm going to from now on be doing all the problems in the videos. That's part of your notes. However, you do not need to go through the entire video. But what I'm going to do going forward is just to tell you what pages I really do want you to listen to the direct instruction. Most of the packet is practice problems for you to do. You can watch the video for those or not, or you can just fast forward and look to see if you obtained the same answer that I did. But going forward, in the beginning of the video, I'll tell you what direct instruction slides that you should listen to the video. In this case, for this section, I want you to listen to the video for all of page 1 and all of page 2 in your handout. That means the first 4 slides here in this presentation. Okay, so what are the objectives? The objectives here are to identify similarity transformations. That, in a sense, is dilations, and we're going to talk about what those are. We're going to verify that we do have a similarity transformation, and of course you may already be suspecting that that means finding proportionality. We're going to draw dilations in class, and we are going to look at dilations on the coordinate plane. So a dilation or a similarity transformation is a transformation, right in the name, and a transformation are things that you've looked at quite a lot in your past. We're going to actually be doing more of it in the future as well. Rotations, reflections, translations. We're going to be taking a deep look at these in a future chapter here. And I know you're very familiar with these already. These are all under the category of congruent transformations, meaning the before and after shapes are exactly congruent in size. In this section, however, we're going to be looking at a transformation that will create similarity or proportional shapes. So those are called dilations, and we're going to take a look at all the details associated with that. You should be aware that there are some transformations that are neither congruent nor similar, and here's just a quick sketch of one. I have a little rectangle here on the left. It undergoes some sort of transformation where we grab a corner and just stretch. And you can see very clearly they're neither congruent and they are certainly not proportional. So today's presentation is mainly here about this center dilations. So what do we need to do to describe a dilation? Well, first let's think about the word dilation. You may or may not associate that with the pupil in your eye. If you are in a dark room, the pupil of your eye is very wide in order to have more light enter. And if you immediately walked out into the sunshine, that pupil would shrink and dilate down. Well, dilation when it comes to polygons is very similar. We're either talking about taking a polygon and enlarging it, or taking a polygon and reducing it. Either way, the enlargement or reducing process would be proportional. So, like all of our previous sections in this chapter, we're talking about proportionality, and we're doing so and describing that with a scale factor. So in order to describe scale factor for a similarity transformation, we need to know what the before image is and what the after transformation image is. And the reason why is because that scale factor is really going to determine whether or not we have an enlargement or a reduction. We use, by convention, a lowercase k as a variable to describe this scale factor. And if we are having an enlargement, in other words, we're taking a shape and enlarging it, we describe that with a scale factor greater than 1. And if we are reducing that shape, then we have a scale factor that's less than 1 and greater than 0. Another thing that we need to describe a dilation is we need a center of dilation. So here in this diagram, the center of dilation is labeled point O, And the center of dilation is a fixed point. In fact, it's the only point that remains fixed during a dilation, about which all the other points are either expanded or contracted. So it's like a reference point. Everything is anchored right to that center of dilation. As I mentioned, we also need to know what is the before, and we call the before shape, before transformation shape, the pre-image, pre meaning before, and you need to know which one is the after transformation. We call that the after transformation the image. So we've got the pre-image and the image. You need to know which one is which, and you also need to know, to describe a dilation, the location of that before or pre-image. In the case of this slide, we can clearly see that we have similar triangles. ABC and DEF are proportional. We could prove that with the sides. We could see all the corresponding angles are congruent, so we know we have similar triangles. So we have ABC is similar to triangle DEF, and we can look at the ratios of those sides and prove proportionality. But there's nothing on this page to indicate to us what is the before or what is the after. So without that information, we're not quite sure if the pre-image is DEF or if the pre-image is ABC. So by convention, I want to introduce you to a new notation here. We tend to show the before and after by using the same labels and just using what's called these prime symbols. So here we have two triangles, and they are proportional, although we'll take a look at that and prove that in a second. But we're told that they are similar, and by convention, the vertices always are listed in corresponding order, and the vertices with the prime symbols, this is prime symbols, that is the after transformation. By the way, we're going to use the same notation for congruent transformations as well. And the vertices, or the shape that does not have the prime, is going to be associated with the before transformation or the pre-image. So that's a convention that we're going to need to get comfortable with and learn to read. So in this case, we know for sure that we have a dilation, and the before transformation is ABC, and the after transformation is A prime, B prime, C prime, and this being a much larger shape is indicating to us that we have an enlargement. Okay, so let's take a look at what's on this chart here. We have a dilation on the plane. ABC is a pre-image, A prime, B prime, C prime is the image, and the center of dilation here is the origin, located at 0, 0. Okay, let's just first take a look at the scale factor. The scale factor K is going to be always written with the image sides on the numerator. Let me change colors here. So the numerator is going to be the image, that means after transformation. And the denominator sides are going to be the before or the pre-image. And by doing so, we can see that the scale factor here is going to be greater than 1. Let's take a look at what we have here. A prime, B prime is 6 units long. We can just read that right off the chart. And AB is 2. And B prime, C prime is 3. And BC is 1. So looks like our scale factor is 3. And A prime, C prime, well, we could take a look at that using the Pythagorean Theorem. We have a side of 3, a side of 6. 6 squared is 36, and 3 squared is 9, so we have a square root of 45. I'm going to simplify that to 3 square roots of 5. And AC is also a right triangle. We're going to use the Pythagorean Theorem. We've got one side 1, another side 2, so we've got 2 squared is 4, plus 1, so we've got the square root of 5. And in all cases here, we can simplify every ratio to 3 over 1. So our scale factor is 3 over 1. It's greater than 1, indicating an enlargement. Now, a dilation is not just an enlargement or reduction, it's also moving this image to a very specific location, and that is completely determined by where your center of dilation is. So how do we find that new location? We start here with the center of dilation, and we would draw a ray going from that center through each vertex of the pre-image, and that ray would be unending, so they just span out in those directions, and the image or after transformation, these A prime, B prime, C prime, are going to fall collinear on that ray. So they're going to fall somewhere on these rays, and the question is where? Well, their location also has a proportional relationship, and in fact it's related exactly to the same proportionality as the sides. So up here we have calculated our scale factor to be 3 to 1. Well, the same proportionality will exist for these distances here along the ray. So let's take a look at an example here. Let's look at C prime to O. So the length here from C prime to O, this length here, we can use the Pythagorean Theorem. We've got a side of 3 and we've got a side of 6. As we saw above, that would be 6 squared being 36 plus 3 squared root 9, so that's square root of 45. Again, let's simplify that to 3 square roots of 5. And the length here of CO is also that same triangle, 2 and 1. So this length here is square root of 5. And the same relationship exists if we put this C prime O or OC prime length here in the numerator, and we put CO in the denominator, we're going to end up with the same exact ratio. And we could take a look at the other sides as well, and the same proportionality will exist, and that will indeed determine where the location of the prime vertices will land. Now, when we're on the xy coordinate plane, there is a very simple way, in addition to this proportionality, to find where the coordinates are of these prime vertices. And in doing so, I'm going to introduce you to a new notation. We're going to be using a lot of this notation when we look at congruent transformations in the near future. If you look down here, if we have the origin as the center of dilation, it makes it very convenient to find the new locations of the image. And I've got D here for dilation, and this XY is really a placeholder for the input. You can look at this as the input to a dilation, or the pre-image, and this arrow says do the transformation, in this case a dilation, and the output locations, or the image, will be represented as such here. So output is the image, and the input is the pre-image. And in every case, you can take whatever the pre-image was, and you can just multiply its location by k, the scale factor, to get the new location. So let's take a look at A and A prime. A is located at 1, 3, and if I multiply 1, 3 by our scale factor 3, I would get 3, 9. And here you can see that A prime is indeed located at 3, 9. And you can go and look at the B prime and C prime using the same technique. Now I do want to caution you that this multiplication of the scale factor will only work if the center of dilation is the origin. If it is not the origin, to find the new location, you would have to use the proportionality of the scale factor. Okay, on example 1, in class we're going to use a straight edge, and we're going to go ahead and draw and measure how to use the center of dilation C here and this trapezoid and look at where a dilation would be located and its size using a scale factor of 3. So we're not going to do this in the video. Okay, so example 1a, determine whether the dilation from figure A to figure B is an enlargement or reduction. Well, going from A to B is certainly a reduction. So A is bigger than B, therefore this is a reduction. Let's look at what the scale factor of the dilation is. Well, we know for reduction, the scale factor is going to be between 0 and 1. So it's going to be greater than 0 and less than 1 for reduction. So let's take a look at corresponding sides. If we look at this side, for instance, here, we have unit 1, and its corresponding side here is 3. So again, we have 3 and 1, but this is a reduction, so our scale factor here is going to be 1 over 3. Let's just verify that we do have proportionality on all the sides. So here we have 2, and over here we should have 6, which we do. And on the hypotenuses here, we have the square root of 5. And here, again, we have the square root of 45, which, if we simplify, is 3 square roots of 5. So in every case, all three sides have the scale factor of 1 to 3. Now the final question is, what is the location of the center of dilation? In this case, we can see that the center of dilation is the origin here. We would draw our rays out, going through all three vertices, and we can actually calculate and verify that we have the same proportionality as our scale factor here, 1 over 3. So let's take a look at this length here from our center of dilation all the way out to this point here. That length, we have a right triangle whose sides is 3 and 3, so that's 9, 3 squared plus 3 squared is 9 plus 9, so that length here is square root of 18. And since we're going from A down to B, the square root of 18 would be in the denominator. And now let's look at this distance here. Maybe I'll change color and make it red. This distance here is from, it's actually the diagonal of a square. And if we look closely at this right triangle here that's set up, we've got one side that's 1 and another side that's 1. So c squared equals a squared plus b squared. That would be 1 squared plus 1 squared is 2. So this length here would be the square root of 2. Would be in our numerator. Let's see if this reduces to 1/3. Square root of 18 is 9 times 2. So we have the square root of 2 over 3 square roots of 2. And they reduce to 1, and indeed that location is absolutely proportional to our same scale factor. Okay, example 1b, determine whether the dilation is an enlargement or a reduction. And what is the scale factor of the dilation? I think part of our question here was cut off. This is supposed to say from P to P prime, and we know that because P prime is always going to be the image, and the non-prime is always going to be the before transformation or pre-image. So determine whether the dilation from P to P prime is an enlargement or a reduction. So P prime after the transformation is larger, so this is definitely an enlargement. And what is the scale factor? Well, we know that K, sorry, I don't like my K there. We know that K is going to be greater than 1 for an enlargement, and we look at the location here. We don't know anything about the side length, so we can't use that to determine the scale factors, but we're going to look at the location in order to determine what the scale factor is here. We see that K is going to equal CP prime over CP, and CP prime is 20, and CP is 8, and we can simplify that if we wanted to, dividing both sides by 4, and our scale factor is 5/2 or 2.5. Mariano wants to enlarge a picture he took that is 4 inches by 7.5 inches. He wants to fit perfectly into a frame that's 400% of the original size. What will be the dimensions of the enlarged photo? 400% of the original size is going to be a scale factor of 4, or 4 times. So we would just take that scale factor we have, I'm just sketching here, if we have 4 by 7.5, we're going to multiply that out, and clearly this does not look proportional. We're going to end up with 16. 4 times 4 is 16, and 7.5 times 4 is going to give us 30, and in both cases these will be inches. Okay, using the origin as the center of dilation, graph the original figure and its dilated image. Then verify the dilation is a similarity transformation. What is the scale factor? So we have clearly triangles here, MNO, and M prime, N prime, and O prime. Alright, so our pre-image is the non-prime. So that is -6, -3 is M. 6, -3 is N, and -6, 6 is O. This is a big triangle, big right triangle. And our image is -2, -1, and N prime is 2, -1. And O prime is -2, 2. I probably should have done this in a different color. Okay, so verify that it is similarity. Well, we would look at the corresponding side ratios. Since we know that the after transformation is smaller, we know that this is a reduction. And consequently our K is going to be greater than 0 but less than 1. So we're going to want always the after transformation sides to be in the numerator. So we're going to have O prime M prime over OM, and we're going to verify is that the same ratio as M prime N prime over MN, and is that the same ratio as ON prime over ON. So let's take a look at the two vertical and horizontal sides being the easier ones. O prime M prime we can see is 3 in length, and OM is 9, and m prime n prime is 4, and mn is 12. So far so good. And O prime n prime here, we've got clearly a 3, 4, 5 right triangle. 3 squared is 9, 4 squared is 16, so that's the square root of 25, so that's a 3, 4, 5. And any time that you have a multiple here of the 3, 4, 5, you know that you're going to have a Pythagorean triple. So you could go through the Pythagorean theorem here with sides 9 and 12, and you will find that this ON will be 15. And indeed, every case they show a scale factor if we simplify it to 1/3. So K equals 1/3. And that is our reduction. Now, in this case, the center of dilation is again the origin here. And we could take a look at all of those rays and side lengths, and we could verify that as well. Okay, which diagram shows the dilation image of triangle LMN with the center point C and a scale factor of 1/3? Well, we know for sure that a scale factor of 1/3 is going to be a reduction. So let's look at our options here on this multiple choice problem. We will see the prime images have to be smaller than the pre-image. So in this case, we have that all three of these, so far so good. Now, I'm not sure at all what this is being shown in D. I want you to always be looking at these rays from the center point coming out and going through all the vertices. So far, A, B, and C are in the running because they're all showing a reduction. However, which one is it? Let's take a look at location first of all. Okay, so we're looking for, to visualize, if we can see that the ratio here of Cn prime over Cn looks like 1/3. So that's what we're looking for. In this case here, clearly Cn prime over Cn is more than 1/3. Over here, Cn prime over Cn is less than 1/3. So by process of elimination and just using our visual skills, it looks like over here in B that the ratio of Cn prime over Cn is roughly 1/3. Okay, let's look at a very important real-world concept here. In this case, we have a light source, and that light source is being used as the center of dilation. So we're going to call this point here L for light source. And this is largely how projection film works. It's also how the projector works in our classroom with the smartboard. So we have a light source and we're projecting an image up onto a board, and in doing so we are enlarging it. In this case we have a puppet, and we're going to be projecting a much larger image of the puppet up on the board as a shadow. So to create the illusion of this light size image, puppeteers sometimes use a light source to show an enlarged image of a puppet projected up onto a screen or wall. Suppose that the distance between a light source L and the puppet is 24 inches. So this distance here between the light source and the puppet is 24 inches. And we want to know, what is this distance here, P prime? How far away do we have to put the board from the puppet in order to take this puppet that in reality is 9 inches tall, and we want it on our projection board to be 49.5 inches tall. So this is exactly how projection film works as well. Well, the closer that puppet gets to the projection wall, so the closer this puppet gets to that projection wall, it's going to become smaller and smaller. So you really want a good distance here to make it large. And as we have learned on the previous slides, this is a dilation, and the locations here are going to determine the scale factor. So the scale factor that we want an enlargement, so our scale factor is going to be greater than 1, and the scale factor that we want is going to be I prime k equals I prime m prime, that's our after transformation, over im. And the location here, that scale factor is going to be exactly equal to the distance here, LP prime, over LP. So we know here we could take this I prime m prime over im, and that scale factor is going to be exactly the same as LP prime over LP. So we can substitute our numbers in here and see that IM we want to be 49.5, and IM of the original puppet size is 9 inches, and LP prime is what we need to solve for, but we know LP is 24. So if we cross multiply here, we get LP prime equals 1,188 divided by 9, and LP prime then equals 132 inches. But we were asked for P prime, which I labeled X. So we're going to need to subtract 24 using the segment addition postulate. So P prime is going to equal 132 minus 24, or it's going to equal 108 inches. And look at doing a dilation on the coordinate plane again. We're going to have a trapezoid pre-image EFGH with a specific set of vertice locations, and we're going to graph that pre-image and the image or after transformation, and we're going to find that location by using a scale factor, we're told, of 1/4. So we know right away if the scale factor is 1/4, we're looking at a reduction because k is less than 1. Alright, so let's take a look at our locations. We're at -8, 4 for E, -4, 8 for F, G is 8, 4, and H is -4, -8. So we have a trapezoid. We haven't studied trapezoids yet, but trapezoids have two opposite sides that are parallel and two opposite sides that are not parallel. And in order to find the location, if we are using a center of dilation of the origin, then we simply need to multiply the pre-image coordinates by this scale factor. So if we multiply -8 by 1/4, we get -2. And if we multiply 4 here by 1/4, we get 1. Negative 4 multiplied by a fourth, we get negative 1. And 8 multiplied by a fourth, we get 2. And so on and so forth. So we can find the locations here of the image. So negative 2, 1 would be corresponding to E, so we would label that as E prime. Negative 1, positive 2 would be F prime. And 2, 1 would be G prime. And finally, negative 1, negative 2 here would be H prime. And you can go through all the same exercise and looking at the size lengths to verify that this is indeed proportional. Thanks for listening. I hope this helps.